Hello everyone, in this video we will be discussing about the last 10 questions of ISRO Scientist and Computer Science question paper. Let's move on to the 71st question now. In this question, we need a 32-bit adder and it is formed by cascading 4-bit carry look-ahead adder, and the gate delays for getting the sum bits we have to carry. Okay, we have to calculate the sum bits. So we in general we know that sum is, if we are adding 2 bits, that is A XOR B XOR C is the sum where C is the carry. Okay, so if we are calculating carry in x seconds, x unit of time, then sum would be calculated in x plus 1 unit of time. Okay, so this is it, and for this we have a formula for carry look ahead adder. For ripple adder also we had a formula. So first we will be discussing about the carry look ahead adder formula. So according to the carry look ahead adder formula, it is 2 cross, that is the delay, the total delay. The delay for sum is the maximum, so the maximum delay is 2 cross L plus 2. Now what is this L? L is the level. Now what is this level? So suppose we have a 4-bit carry look ahead adder. Okay, it is a 4-bit carry look ahead adder. So for a 4-bit carry look ahead adder, from this we need to make a 32-bit. So we would be needing 4 cross 8, that is 8 4-bit CLA to construct a 32-bit adder. So the level is 8. 8 levels of 4-bit CLA would be needed here. So we would be putting the answers over here, that is 2 into 8 plus 2, it is a 16 plus 2 is 18. So 18 is the answer here. This is a formula, but let's move on to the concept first. Okay, this is a formula for carry look ahead adder. We have a formula for ripple adder also. It can be asked, in case of ripple adder, what would be the delay for 16-bit, or what would be the delay for a ripple adder of 12 bits, and so on. So the answer for ripple adder is, it is 2n plus 2 gates. It is the gate delay for ripple adder. And for carry look ahead adder, it is 2 cross L plus 2. Here the L is the level, and here the N is the bits. That is, if it is 8-bit adder, it would be 2 cross 8. So we are having 32-bit adder, it would be 2 cross 32 plus 2. Okay, so it is 64, 2, it is 66 would be the answer for if it was a ripple adder. What CLA? It would be 18. Okay, so let's move on to the concepts. Okay, the one thing for CLA, the delay for carry is 3 gates, and that for sum is 4, that is 3 plus 1. Okay, 4 gates. It is, you have to remember, or you have to study the carry look ahead adder in deep, so you would get these things. Okay, now let's move on. Here we have 8 carry bit 4-bit adders, that is 1 2 3 4 5 6 8 adders. Okay, so what, the first adder, the carry would be generated at 3 unit of time and sum would be generated at 4 unit of time. Okay, so meanwhile the sum is being generated over here, the carry would be generated. So it would take 1 unit of time less, so it would be generated in 2. Here would be 1 unit of time less 2. So 1 unit of time less 2, 1 unit of time less 2, 1 unit of time less 2, 1 unit of time less 2. Okay, the final carry has been generated, but the sum would be generated at 3 only. At 2 unit of time the final carry has been generated, carry final, but the sum would be generated after 3 unit of time only, 1 unit greater than the carry only. So this would be 3 plus 2 is 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 is the answer. Okay, this is a concept behind this, but you can remember easily by this formula, that is 2 cross L plus 2. Okay, and what if here it was the carry bits? Here in case of sum, if in the question it was the carry bits, the answer would have been 17, because instead of this 3 you would be adding this 2 over here, so answer would be 17. Okay, let's move on to the next question. 18 is the answer for this question. Next question, we consider the addition of 2 complements number. Okay, there is a 2 complements number and 2 complement addition we are performing. These are the 2 numbers. Okay, this is the most significant bit of the both number, that is the MSB. Okay, and this is the least significant bit. And binary adder for adding two unsigned binary numbers is used to add two binary numbers, and the sum, this is the sum. This is the sum, and this is the more significant bit of the sum. C out is the carry out, and the overflow condition is defined by. Okay, now what is the condition for overflow in 2's complement? Condition for overflow in 2's complement is if two positive numbers are added, okay, and result is negative, then overflow is there. Okay, second is if two negative numbers are added and the result is positive, then also there is a overflow condition. So these are the conditions for overflow in 2's complement. Okay, you have to remember, after adding two positive numbers, if the resultant is negative, then it is overflow. After adding two negative numbers, if the resultant is positive, then it is a overflow. Okay, see, this is the sign bit. The most significant bit is always the sign bit. So this is the sign bit, bn minus 1, and an minus 1 is the sign bit. Okay, so I'll write here bn minus 1 and an minus 1. Okay, if the both are 0 and cn minus 1 in the sign bit of the resultant, so I'll be writing it as cn minus 1. If both are 0 means both a and b are positive and this is negative, then there would be overflow. Okay, when both are negative and this is positive, then there would be a overflow. See, it is like this. So from this we can conclude an equation like a n minus 1 bar into b n minus 1 bar. Okay, a n minus 1 bar into b n minus 1 bar into c n minus 1. Okay, this is 1 plus a n minus 1 bn minus 1 into cn minus 1 bar. So this should be our answer. Let's see whether it is in our option or not. So no, it is not in our option. This is not our option. Okay, this is also not our option. This can be our option. Let's check. It is an minus 1 bar. No. See, this portion is right. This portion is right. That we have here an minus 1, bn minus 1, cn minus 1. But here this bar should not be there. So our answer can be B, but no other option is right. In ISRO, this question was excluded for evaluation because the answer options were given wrong. So if this wasn't there, then B can be our answer. Okay, so you have to remember this, what are the overflow conditions. Next question. Okay, consider a function. So we have a recursive call, x is the input, which is equal to 95. This is the given input, and we have to tell what is the answer. It is a recursive call over here. Okay, so let's check. Okay, first for x is equal to 95. So for 95 you would be check the condition. 95 it would be over here. For 95 you would be checking the condition, and 95 is not greater than 100. X is greater than 100. So 95 is not greater than this would be called. So it would be like f of 95 is called first, and after calling f of 95 the else condition is executed. Okay, then we would be having f of 95 plus 11 is 106. 106 we would be having. Okay, after that it is a recursive call. Okay, so when this f of 106 is called, 106 is greater than 100, then this would be executed. Then this should be f of 96. Okay, when f of 96 is called, then this would be executed, and this would be equal to f of 96 plus 11 is 107. So this is like this. Now 107 is greater than 100. 107 minus 10 is 97. Then it would be f of 97. Till now our answer is not there, neither 89, neither 90, or neither 92. So 97. Then after that we would be adding, when 97 is called, then that means else part will be executing. It would be f of 108. Okay, when 108 is called, it would again go to f of 98 because there is minus 10. 108 is greater than 100. Okay, then it would be f of 109. Okay, f of 109, because when 98 is called, else would be there, 98 plus 11 is 109. So when f of 109 would be called, we will be subtracting 10 from this, so it would be f of 99. Okay, and then it would go to f of 99 plus 99 plus 11 is f of 110. F of 110, then it would be minus 10. 110 minus 10 is f of 100. Okay, f of 100. 100 plus 11 is f of 111. Okay, then it would be go to f of 101, because minus 10, and f of 101. When f of 101 is called, then it is 91 is the answer. So answer should be C. That is 91. 91 is the answer. Okay, next question. Consider the function. We have, it is a function. Okay, in this we have initialized an integer over here. We have a loop. We have incrementing. There is a right shift. This is a right shift. Okay, we have to return the count. We have to return the count, that how many times the right shift has been done. Okay, the number for which right shift has been done is 435. So when we right shift is generally divide by 2. So there are two ways of solving this question. I'll show you. First way is the easiest way, I think so. We have to convert this into binary. Okay, so when I convert 435 into binary, I would get 110110011. Okay, so we are shifting it right. Okay, so first right shift, count is equal to 1. Inside the loop, we are inside the loop, count is equal to 1, and we are shifting it. Okay, we are shifting it. Then count is equal to 2, then we are shifting it. Then count is equal to 3, we are shifting it. Count is equal to 4, then we are shifting it. Count is equal to 5, we are shifting it. Count 6, shifting it. Count 7, shifting it. Count 8, shifting it. Count 9, shifting it. Here it would be 0. So while loop would end, and return count is 9. So 9 should be our answer. Okay, this is the first way we can convert it into binary and we can solve it. Else you can solve it by like this, in decimal form also. 435 is the first number. It is divided by 2 is 217. Divided by 2 is 108, divided by 2 is 54, divided by 2 is 27, divided by 2 is 13, divided by 2 is 6, divided by 2 is 3, and 1. So it is 1, 2, 3, 4, 5, 6, 7, 8 and 9. So 9 is the answer. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 is the answer. Okay, so by this you can directly divide it by as a decimal number, divide by 2, or you can convert it in decimal and you can run a loop over it. Okay, next question. In IEEE floating point representation, the hexadecimal number this corresponds to. Okay, so first we would be converting. This is hexadecimal number, so every digit would be a 4 digit number. So it would be written like this. This is 0. This is 0, 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 and this is C. Okay, and in IEEE floating point representation, first bit is the sign bit. So this 1 is the sign bit. So our number is negative. This I know. First bit is the sign bit. Okay. Now, for what about the next 8 bits? That is 1, 2, 3, 4, 5, 6, 7, 8. Next 8 bit is the exponent. Okay, and the remaining 23 bits would be remaining here, and remaining 23 bit is Mentisa. Okay, and IEEE floating point representation is a biased floating point representation is a biased exponent system. Now what do you mean by biased exponent system? Is the biased exponent value is 2 to the power exponent minus 1. Okay, so 2 to the power exponent is 8, so 2 to the power 8 minus 1, 2 to the power 8 is 128, 128 minus 1 is 127. So the bias is 127. So it is written as minus 1 to the power sign bit, okay, into 1 point Mentisa into 2 to the power 128 minus 127. 2 to the power 128 minus 127. So it would be minus 1 to the power 1. 1 point Mentisa is 0. See all zeros. Here it is all zeros. So Mentisa is 0 into 2 to the power 1. It is minus 2 is our answer. So D should be our answer over here, minus 2. Okay, next question. Which of the following set of components is sufficient to implement an arbitrary Boolean function? Okay, so before going through this, we need to know about the universal gates. What are the universal gates? NAND and NOR. Universal gates are the gates which are sufficient to implement any function. So NAND is made up of AND and OR, AND and NOT, and NOR is made up of OR and NOT. So if we can simplify these gates into AND and NOT, or NOR and NOT, OR and NOT, so that means or NOR and NOT, that means these would be capable of doing so. Okay, so the first is XOR and NOT. So by using XOR and NOT, we can make XNOR and XOR. But we cannot make AND or NOT, AND or OR. We can make XOR, but we cannot make AND or OR. So this option is wrong. So it is not functionally capable of implementing all functions. Okay. Next is AND gates, XOR gates, and 1. Okay. So this is XOR gate can be used. By using the XOR gate, we can make a NOT gate. That is, A XOR 1 is A bar. So by using XOR and 1, we can make a NOT gate. Okay, so AND and NOT is a universal gate. So option B is a correct answer. Okay, next we have 2 cross 1 multiplexer. Okay, by using a 2 cross 1 multiplexer, if we have 1 and 0, both 1 and 0 as an external input, then this option would have been right. But here we don't have 1 and 0. A 2 cross 1 multiplexer is complete if it's universal if it has 1 and 0 as the external input, but we don't have 1 and 0 here. So this option is also wrong. 3 input gates that output A dot B plus C for inputs A, B, C. So in this, if I put C is equal to 1, then I'll get an AND gate. Okay, if I get B is equal to 1, then I get a OR gate. But no NOT gate. NOT gate is important, so this is not also, it is not also false. So the answer is B, because by using XOR and 1, we can make a NOT gate, and 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 NOT becomes NAND, and NAND is a universal gate. So answer is B. Next question. Okay, we have to match the following. So it is like which of them are white box, which of them are black box, which of them are system, and which of them are performance testing. So let's see what are white box testing techniques. Okay, white box testing, it tests the internal structure or working of an application. It covers the following. So all control flow, data flow, branch testing, statement coverage, decisions testing, modified condition testing, prime part testing, and part testing. These all comes under white box testing. Okay, it all comes under white box testing. So next, you have to remember this. Next, black box testing techniques, it includes decision table testing, all pair testing, equivalence partitioning. See, equivalence partitioning is there, it is black box testing. Okay, boundary value analysis, caution effect graph, and error guessing. These are our black box testing techniques. Okay, now see, our answer is this A, because we all know that the condition testing, it comes under white box testing. We learned that. And equivalence partition comes under black box testing. Okay, and performance testing is volume testing, and alpha and beta testing both are system testing. Both alpha and beta testing are system testing. Okay, they are tested when everything is completed. It is a system testing. So answer is A. Next, consider the result of medical experiment and aims to predict whether someone is going to develop myopia based on some physical requirements and heredity. Okay. So the decision has to be made that they would develop a myopia or not based on some physical requirement and heredity. In this case, the input dataset consists of personal medical characteristics and target variable is binary. So we have it in the form of tree, that is 1 and 0. 1 if they have likely to develop myopia, and 0 if those are not. This can be classified as, so it is very clear it can be classified using decision trees. So because association rules is if then else rules, so we cannot use this. Clustering is also, it cannot be used, and regression, no, it cannot be used. The decision tree is the answer. Which of the following related to snowflake schema is true? Okay, so let me first tell you, snowflake schema is related to star schema only. It is the extension of star schema. So this statement is false, not an extension of star schema. Let's see what is snowflake schema first. Snowflake schema is the extension of star schema. Yes, it is the extension of star schema where each point of star explodes to more points. Okay, now maintenance efforts are less. It is false because here it is each point of star explodes to more points. Then that means we have more database to maintain here. So it is false. In star schema, each dimension is represented by a single dimension. Each dimension is represented by a single dimension table in star schema. Star schema. So it is for star schema. It is not true for snowflake. Whereas in snowflake schema, the dimension table is normalized into multiple lookup tables. So we have normalized dimensional tables. So the answer is C. So you have to remember this. Snowflake schema is the extension of star schema in which stars explodes to many points and they have normalized dimension tables. Okay, so C is the answer. Next question. Consider the following C function. We have a C function over here. In this we have a array of characters and we have a pointer to a character and we are printing something. So we have to tell what is the output. What is this? So let's see. Let us take it like this. Okay. So if we have this array C, so if I only write C, so C would point to this. Also P is the pointer to this array. So P would also be pointing to here only. Okay, this is a question. Now what we have, this is the index 0, 1, 2, 3, 4, 5, 7, 8, 9. This is the index. Let me check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Something is missing. Okay, this is our index. Okay, the 2 and P are pointing to this. Our next is 2P. So 2P is this, P of 2. So you have to know that this is equal to P of 2 and this is equal to P of 6. Okay, 2P is this. Okay, so 2P or P of 2 is, sorry, this is P of 3. P of 2 is this. Okay, so 2P is R. So we have P of 2 is equal to R. Similarly, P of 6 is equal to I. This is P of 6. Okay, P of 6 is equal to I. So now we have, this is R minus I. So R minus I is 9. Because I, J, K, L, M, N, O, P, Q, R. So 1, 2, 3, 4, 5, 6, 7, 8 and 9. So R minus I is 9. Okay, this is 9. Okay, so now we have here C plus 9 minus 1. Okay, so we would be having C plus 8. So from A we have to count C, we have to go to 8. So C plus 8 is this. Okay, and we are printing a string. So 1 and 7 would be printed. C plus 8, we are printing a string of C plus 8. So from 8, 1 and 7 would be printed. So answer would be this, D, 17. Okay, so this was the last question of a question paper. All the best, work hard, and please subscribe our channel if you like it, and thanks for watching, and please click the like button also.